So good afternoon, everyone. Welcome back. We have a few people taking their seats quickly. It's my great pleasure and honor to introduce our next speaker. See how good my Polish pronunciation is. Janusz Hołyst. Professor Holyst has been a pioneer in fields which probably did not have a name when he started in them, but we now call things like econophysics or social physics, pioneering the use of these methods to understand more of the social studies and the humanities. His ability to take our conventional understanding and bring it forward through the addition of just the proper proportion of novelty, as we learned this morning, can be witnessed by the over 2,100 citations he has in the literature, by the approximately 15 international conferences he's been able to help organize, playing a major role in that, by his position as an editor on several prestigious physics journals, and hopefully from what he'll give us today in this talk. So, without further ado, here to tell us more about orders of hierarchies and hierarchies of order, Professor Holyst.
Mr. Chairman, ladies and gentlemen, let me first thank the conference organizers for inviting me to this very interesting and very important meeting. I have added subtitle to my talk, from theology to physics of complex systems, since I start with some concepts that in fact possess roots in theology, in history. So this is the plan of my talk. First, I will try to explain that we have different kinds of character. There is no unique definition of this extremely important object of this phenomenon in some way. Then I will describe more in details inclusion and order hierarchy, and come to the concept of induced hierarchy due to special interactions in the systems. The systems will be weakly coupled networks. Then I will present you results on the role of information for buildings of hierarchy. And I will end with the model where the hierarchy is built from bottom to up. So, as I already said, the roots of meaning of hierarchy come from Catholic religion, and it was already nearly 1500 years ago when for the first time this concept was used by Catholic philosopher and priest, pseudo Dionysius Daurogite, sorry for my pronunciation. And the meaning of this word at that time was came from Greek language, chaos, sacred, archaea, rule. So the governance of things that are sacred. Pseudo Dionysius introduced the concept of orders between different chorus of angels. And from that moment, okay, so this is the picture, illustrate there are several groups of spiritual objects that are also ordered in some way, and this was called hierarchical system. And from this moment, people started, at least we believe that it was their moment, on something like the order that we can go, okay, consider Catholic religion, the Pope, cardinals, and so on. And this concept then was moved to non-Catholic and not religious communities. So also the people who ruled the the society who ruled the nation, said we are at the top, there's a king, lords, and so on. And up to now we follow this concept saying that we have directors, vice directors, and leaders of departments, and so on and so on. This kind of hierarchy is called control hierarchy. Why? Because it means the agent that is at the higher level is able to control all agents that are at the lower levels. But this is not the only meaning of the hierarchy. The second meaning is so-called, is the called order hierarchy. So the first was the control, now is the order. It sounds similar, but it's not the case. Order in the sense that we have some objects, for example, it could be companies, cities, where we can label this object by some numbers. Because it can be also words, for example, and the numbers then are the frequency of occurrence of the words in an sample. And if we are able to order any objects, we can call it kind of order hierarchy. And there are interesting features of this kind of ordering for many systems. For example, it is well known that if we study language, we have famous zip flow, since we can calculate how many times the word that is at the first place is cited in a given document. This is the case of this document is a large document, it's a corporate Polish language, and the mostly cited word is W. It means translated to English in. Next, then we have next words at the next positions, and if we calculate the frequency of occurring of these words, we receive famous zip flow, power law behavior. In this case, this is typical exponent, this is around 1. And it is important to say that this kind of ordering is equivalent to the Pareto law, since the probability of the frequency that we meet in and search an object that is cited here, for example, with the frequency C, this follows from the zip flow where both exponents, there's well-known relation between both exponents. And this kind of order hierarchy was observed in many systems, like ranking or ordering of firms according to the income, well, to use the scaling that you can see. And this, from this, we see once more the Pareto law of probabilities distribution, ordering of cities according to the number of people that live in a given city, and so on and so on. And all these laws related to the ordering of some objects, if we are able to order them, it means we need to have some numbers to order them. All these, many of these laws are power laws, and here this is the case of so-called Gibraltar law. The third kind of hierarchy is so-called inclusion hierarchy. It's completely different in some way, because inclusion hierarchies, we have a large system that can be divided into several subsystems, and every representative of the subsystem can be divided to the smaller pieces and so on. United States consists of several states that can be divided into counties and so on. Or if we have our computer, we divided it to directories, subdirectories, and so on. there's no dependence. It's only inclusion dependence, but there's no order dependence between these elements, of course. Most interesting for physicists, and not only for physicists, is so-called level hierarchy. It is similar to the previous one, in the sense that there are different levels of organization, coming, for example, from cellular level to the tissue, organs, the whole animals, and the whole societies. The difference between inclusion and level hierarchy is that usually there's self-organization that is responsible for forming the next level. And this is non-trivial, and as far as I know, this is a main challenge probably for, not only for physics of the complex systems, to find a universal rule that governs the principle of emergence of the next level of organization. And of course, for us, for human, the issue is there in the next level here, higher than our society. And here it's important to understand the role of interactions inside the community, inside the level, and probably interactions with the environment, because the whole evolution is, as far as we understand, is driven by the environment, by the net entropy coming from sun. Typical feature of hierarchical system is the presence of many scales, like here it is many scales in time and many scales in the space, from nanometers to several thousands of kilometers. If we consider inclusion and order hierarchy, we can use the concept of wiki-coupled networks. Wiki-coupled networks are systems of networks that are relatively densely connected inside, and there are space links between such units. And of course, there can be several levels of such a organization. And here I will present you some simulations, because this inclusion hierarchy can be also related to induced control hierarchy. I will present you the example of Ising dynamics of coupled networks that some way it's a very naive model representing interactions between two social networks. So imagine we have two social networks. Okay, I will try now to switch to the simulation. I pray it works. Okay, as I said, it's a very naive model of social dynamics. We have two separated at the moment networks, and there is a kind of Monte Carlo metropolis algorithm responsible for flipping of spins inside both subnetworks. This is the Ising model, spin 1/2. So the blue and red means we have spin up and spin down. Networks are separated at the very beginning. This network, I would call it yellow network, because there are yellow connections. And there are 30 nodes in this network and 158 links. This network is larger, and I will call it green network, because there are green connections. There are 50 nodes and 94 links. Here you can observe mean opinion or mean magnetization in both subnetworks. You can observe also here fluctuations in both diagrams. You can see that in the green network these fluctuations are larger, and in fact this green network already was flipping to another stage. Now I stop for the moment and try to think what can we expect if we connect both these subnetworks. At the moment that when I stop the simulations, both subnetworks, the sense of social dynamics, possess different opinions. This yellow network follows mostly the red opinion, while the green network follows the blue opinion. And, well, one can naively think the larger network, it means the network, the green network, is the network that could control this smaller network if we connect it. We observe that this is not the case. I will put the temperature smaller, and I will start once more. And now I will connect, I'm connecting the networks. Oh, yes. So you could observe there's a jump in this network. Now this larger network, this larger community, follows the opinion that was previously the opinion of the smaller community. And this is because that not only the size is important here, but also the density of links. But not only the density of links is important. I will now show you the next experiment. Now I select a few leaders in this yellow networks. These are the nodes with the largest connectivity. And we'll try to force them to change their opinion to the yellow, to the blue one. I will select just 3 leaders. You can see these 3 dots. And these 3 leaders are now influenced by the external impact, which is opposite to the general opinion in their group and in another group. Okay, maybe I will put this impact a little bit larger. Okay. And you could observe they already have changed their opinion. And if we have a good one, the temperature should be higher. Oh, okay. The temperature hub here, the transition. So you could see, influencing only 3 members of this community by the external impact. If we look to the tails, you could see that first there was a jump in this smaller community, in this yellow network, and then in 2 time steps, the jump of the larger community. So we can control the whole system just by influencing only a few important representatives of this smaller community that is denser, that is larger, that is better connected, better organized, and can control larger community. Is it an accident or not? We can try the reverse experiment. Politicians are changing their opinion, I observe. Probably we need to wait for some fluctuation. I will help with flow. Okay, the larger is the temperature, the faster is, of course, is the transition, because all of this is governed by the fluctuations. Okay, suppose we do not know the topology of the system, because the people who work on complex networks are able to calculate some values coming from topology of the network. That values can give us hints which of these networks is the leader and which is the follower. Suppose we have no access to this picture, because this is a typical situation, and we can observe only this picture. Are we able to forecast that who is the leader and who is the follower? If you know the rules of statistical physics, you are able. The network that is this yellow network exhibits only small fluctuations, and so in this sense it is more stable. And this is well-known theorem in statistical physics, fluctuation dissipation theorem, that shows us the so-called susceptibility is proportional to fluctuation. So if we have large fluctuations for this network, for this green network, this network is more susceptible to external influence, to the influence of the second network. So it is not only the topology that it can give us information about the induced hierarchy in such a system, but also the magnitude of fluctuations. However, in fact, the scenario is even more complex, because here I connected both these networks quite randomly. One can, if I had more time, I could show you the scenarios that when we connect, for example, links to the leader, we can attack the leader in this network by many links from another network, and in this sense, the leader will become the leader of the another community. So not only the number of connections, but the way we are interconnecting such subnetworks decides on the induced order of the control in such a system. How much time still I have?
You still have about 10 minutes?
10 minutes. So we could observe that the smaller but denser connected community can dominate a larger one. So this is a kind of induced control hierarchy. This is also related to discontinuous changes in the system observables. If one can show for infinite systems, this is first order phase transition. Now I will come to the next topic from my talk. This is the role of information for top-down growing hierarchy. The motivation is follows. In growing social groups, at the very beginning we have the leader of the community. New individuals try to occupy the best place in the existing social structure, in the existing social hierarchy. However, we are never completely informed. We have a limited fraction of the society where we can ask to be linked to the new community. So we have a limited information. And the aim is to check how the size of this available information influence network topology, or more precisely, how it influences the number of hierarchy levels that emerge in such a system. So what is information? If you drive highway, if you get this sign, you have information, you are getting information because you can make a useful decision. So information for us is used to make decisions. If it is, cannot be used for any decision in some way, it is worthless. A decision leads us to some actions. Imagine we introduce the following concept of information and the decision, that the information versus the logarithm of the number of options we have. It is similar to microcanonical ensemble definition. It does have sense since if we enter the restaurant, and this is the list of drinks, are we getting information or not? I suppose this is not the information because we have no possibility to decide. This is only one beer, so there's no choice. And in fact, information defined in this way is easier. Imagine the following system. Imagine we have, for example, large project, kind of coordination action, lasting for several years, and there is the leader of this project, and it's something possible that new partners can enter the project. So the new partners would like to have as the position that is the best for them. And this structure can be called perfect hierarchy. You have a kind of root, project leader, and several levels like leaders of work packages, tasks, and so on. So imagine we have a new guy, a new professor who would like to join this coordination action. And this professor is interested in the topic and would like to write a letter to somebody who could introduce him to the community. As I said, we have always limited size of our information on the community. So this guy, assume, has access only to these 3 members of this community. M is the size of the group where these potential new members can select a person who would introduce him or her to the community. If this is the case, it is, in fact, this is the group, then of course the selection is trivial. The guy will write a letter to this person, and if it's accepted, it will enter the community at the next level. Why? Because it will be linked directly to this member of the society. And this is all. So this is all regarding the dynamics of our model. So this is the growing network. As a matter of fact, this is not even important, it's a network. It's a system of levels. And we are occupying these levels by next agents. So it's growing and growing. And we are asking how many levels are in the system. Because at the beginning there is only one level. What is the occupation of different levels? And about also other observables. So we have considered 2 versions of the model. In one was a limited size of what we call the tournament. This M was constant. It reflects limited availability of information. And one is constant, and in the second case, M was growing with the size of the community. In fact, it is equivalent to the Poissonian selection. We call it Poissonian. The first case, constant and limited. In the second case, the information is growing in time. So now, if we have this system, how many levels will occur if in the system are some number of agents? What is the birth time of a level of number 2, 3, and so on? This is the question that in natural way one can ask. So what we have observed, if M is 1, so in this sense there's no information in this process at all, like in this case of the histogram. Then we can calculate precisely what is the number of agents at every level. This is governed by this equation. Interesting feature of this solution is the following. Hierarchy levels that are born earlier grow slower after some time. So here you have, for example, the occupation of the first level of the hierarchy, the second, the third, and the 10th. You can see after, at the beginning, of course, the first level is dominating. There is a period of time when the third level is dominating, 10 level, and so on. So every level of organization in such a system follows from this simple equation. It follows also from numerical simulation. Possesses its, as a golden age when it's dominating in the sense of occupation the whole system. And this is the number of character levels at time. It is going approximately as this equation. And you can see the larger is M, the larger is available information, the slower is the increase of number of characters. So information limits the building of many hierarchical levels because the people well informed are trying to find the best position very high in the community. Very different situation is in this Poissonian model. Now the information is growing logarithmically in time. And you can observe that there are only few levels of organization. Here you can see only first, second, and third level of organization. Because these three levels, they monopolize the whole system. In fact, in this system, if the information is growing logarithmically in time, the number of hierarchies is limited in time. It's not growing logarithmically as before, but there are only a few levels of hierarchical system. The larger is this alpha parameter that describes the size of information. The smaller is the number, the effective number of hierarchies in this. So this is for comparison, both kinds of models. If the information is limited, constant in time, we have many levels of hierarchy. If the information is growing at least logarithmically in time, we have only a few levels of hierarchies because every next agent is finding a place here and where here, this or this position. I suppose I nearly took all my time and only say that we have also developed another kind of model where we simulated the situation where the hierarchy is built bottom up. This corresponds to the people working, for example, in the communities like Wikipedia or Ubuntu, and they had to organize themselves from bottom to higher levels. And we also got results
for agent simulations and for analytical calculations based on master equations. I think I will leave, okay, this is a kind of simulation for this system. I need to come to the summary. So for hierarchical systems, we can consider several types of hierarchies. This is first message. Control, order, inclusion, and level. And one can think also that at least control hierarchy can be induced by additional interactions in the system. And I have shown you in the case one model when the hierarchy was built top-down, and the second just only mentioned that we are also able to consider this opposite situation. Thank you very much for your attention.
Okay, so we have a few minutes for questions. If I can take the first one just to lead things off. You showed that based on differences of information, we'd get either a very deep hierarchy or a very shallow hierarchy. How much information is there, do you think, in the academic community?
This is a very good question. Thank you very much. So, if we are talking about our academic community, so if we have no access to the information, or very limited access, then as the result, then we have many levels of hierarchy. If this access is more common, it means that there should be smaller levels of differences. For sure, in real social systems, it is much more difficult to say, I'm at this hierarchy level, because at the moment, for sure, you are above me. And our leader, our conference chairman is higher than you. Social systems are much more complex than the naive model that I introduced you. Message is information, larger amount of information limits building hierarchical systems.
Other questions? Okay. Well, we can have one last round of applause to thank our speaker.
Thank you.